Good morning. All right. Welcome to GitHub Satellite. We are so happy to be here with you today in beautiful Berlin, and we have quite a show for you today. Welcome to the 800 people who are able to be in the room with us today, and to the thousands more who are watching online. This is a really exciting time for us to be at GitHub. More people are joining GitHub every day than ever before. And so the audience here today represents the more than 36 million developers who call GitHub home. Now, today we have a lot of great blockchain announcements. I'm just kidding, there's no blockchain announcements. We have a lot of great announcements to show you in 3 different areas: security, enterprise, and community. We're going to show you the work that we've been doing to make software development more secure from end to end, to help better support and serve large organizations and enterprises, and to serve open source maintainers and contributors. But before we get into all of that, let's take a step back and talk about what's really at the heart of GitHub, which is the open source community. Every day, developers around the world make millions of contributions to open source projects on GitHub. And we thought it would be interesting and fun to take our data set of that contribution stream and actually visualize it on a globe. And that's what this is. Every little ray of light that you see coming out of the Earth and going into space represents one contribution to an open source project from someone somewhere on Earth. And I think it's so cool. This is real data. It's over 100 million contributions over 30 days being visualized here. And one of the things that immediately stands out for you when you look at this is how global our community is, right? More than 80% of the contributions that occur to open source come from outside the US. So in a way, if your company or your team is using open source code, you've already embraced remote work. Now, the chances are you have already started to use open source code, because nearly every software project on Earth today has open source dependencies. So whether you're working at a large company or a startup, whether you're a scientist or a student, you rely every day on open source code, and you rely on the people who create it, right? Every line of code that you write builds on the work of thousands of others. And you can think about it this way. When you import an open source library into your code, you're not just adding code to your project, you are effectively adding a team of developers to your extended team. You're actually almost giving them commit access to your code that you then put in production. But then you also get to benefit from the work they're doing every day to improve their packages. So this is the reality of building on open source. And if anyone wants to make an editor extension that does this, I think that would be really cool. But still in our heads, we have this stereotype of the solitary developer, right? When we think about the act of writing code, we often think about a developer alone in a dark room, right? It's just them and the computer writing code, and you slip pizza under the door, and it gets converted into code and uploaded to the cloud. That's still a mental image that we have when we think about developers. But in reality, software development is deeply collaborative, right? We're all a part of an interconnected community of developers. And this morning, I'm going to tell you a story about how thousands of open source contributors work together to help create a major scientific breakthrough. This is the first ever picture of a black hole. It was published just last month, and more than 4.5 billion people around the world have seen this image. It's very famous, and it is a huge landmark achievement, right? Scientists have theorized about black holes for decades, but this is the first time we've ever actually seen one. And this one is at the center of a galaxy called M87, which is really far away. It's 55 million light years away from us here in Berlin today. And the scientists who created this picture used a global network of telescopes to generate a huge amount of data, which they then composed into this image. They spent years processing that data to get this image. And this is the moment of truth, right? This is Dr. Katie Baumann, one of the lead developers and scientists on the project, and one of my personal heroes. And this has become an iconic photo of this landmark human achievement. I love this photo because as developers, we can all identify with this feeling, right? It's that moment when your code finally just works, when all your tests pass, when all your hard work kind of comes together. You look at it and you feel that same feeling yourself. And it also makes you wonder, too, to look at this picture, right? Like, what did it take to get to this point? What was involved? What was the math and the science and the algorithms that were involved in getting here? And then, what's going on that chalkboard in the background? There's a triangle there. I have so many questions when I look at this. And so here to answer those questions, please welcome, via satellite from Boston, Massachusetts, Dr. Katie Baumann. Katie?
Hi, Nat, and hello to all the satellite attendees. Thanks for having me.
Katie, we are honored and thrilled to have you join us today. You're in Boston right now, and it's nearly 4 in the morning there.
Yeah, I really wish I could have been there in person.
Well, you're a busy person, Katie, so thanks for taking the time to join us in the middle of the night. Can you tell us a little bit about what it took to produce this image of a black hole?
Yeah, of course. So taking the first image of a black hole was a huge endeavor and took many people years of hard work in order to build the computational telescope that made it possible to see the unseeable. Because the black hole we looked at is so far away from us, it's 55 million light years away, it appears incredibly small in the sky. So it's about the same size to us as a grain of sand would appear in Los Angeles when standing in New York. And because it is so small, we needed to build an Earth-sized telescope in order to resolve the ring of light. But since we couldn't build a single-dish telescope the size of the Earth, our collaboration instead spent over a decade connecting telescopes from around the world using the precise timing of atomic clocks. And making an image from this telescope required that we not only develop new instrumentation, but also design algorithms to process and interpret the collected data to form the image. And this required the expertise of a global team of over 200 collaborators who worked on developing cutting-edge instrumentation, data processing, theoretical simulations, and analysis. So my primary role in the project has been using techniques from both astronomy and computer science in order to combine information from the telescopes around the world to construct and verify that black hole image.
Now, Katie, that's awesome. It's so wonderful to hear that from you directly. Now, I have to say, this picture of you has become so famous, and I think part of the reason is the obvious sense of delight and that kind of feeling of eureka, that you have in that moment and that every developer knows a little bit. What do you remember about that moment?
Yeah, definitely. So this was really an amazing day. It was a hot day in June. The data had just finally been released to us for imaging, and our collaboration decided actually to split ourselves into 4 teams. And by splitting ourselves into teams and having each team independently make an image, we avoided a shared human bias in our results. So anyway, when the data was released to us, some of the members of the team I was on, Team 1, ran into a small room and we got ready to make an image. So we all had imaging scripts that we had each developed on our computers, and we decided to press go at the same time on all of them. And so it was really amazing seeing the picture just start to appear on our screens. And this picture was taken as that was happening. And I was just flipping between awe, disbelief, excitement, and also just praying it wasn't some sort of cruel joke and it wasn't really fake data. But most of all, I think we were just so proud of what our collaboration had been able to achieve together, and it was really an amazing day.
So Katie, describe the scene a little more. What is this room that you're in? Were you in Boston, Massachusetts, where this photo was taken?
Yeah, this picture was taken in Cambridge, Massachusetts, in the office of the EHT director, Shep Dolman. And this is a building where a number of us actually spend a lot of time working together. But the funny thing about this photo is actually it's impossible to see Andrew, my collaborator. So unlike the M87 black hole image, which was truly a collaborative effort, Andrew can claim sole credit for snapping this picture of me as he sat next to me making a picture of his own. And similarly, on the other side of the table were a number of other team members, and many others in rooms around the world were doing the exact same thing.
A lot of your other team members, like you mentioned, Andrew, have become kind of famous and celebrated in their own right for their work on this project as well. And in fact, we have another surprise for the audience here today, Katie. Do you want to do the honors?
Yeah, Sure. So actually, 6 of my colleagues from the team are there in Berlin at the conference with you all.
Come on out. Let's give them a big round of applause. It is so awesome to have the core team that worked on the software behind this black hole image here today. I can't tell how much we're all nerding out over having you on stage. Why don't we go down the line and have you each introduce yourselves and just say a couple words about what you worked on.
So I'm Andrew. I work on imaging, so designing sort of software to experiment with, test, and validate new methods for converting the EHT's challenging data into images that we can interpret.
I'm Kazu. I'm the primary developer of one of imaging software packages and also developing new imaging techniques that created the first ever picture of black hole from the calibrated telescope dataset.
Hi, I'm Sarah. I work on data calibration, primarily on modeling the behavior and sensitivity of all the different telescopes in our network.
Hi, I'm CK. I architect the cloud computing infrastructure for the EHT, and I scale our algorithm and develop simulation software.
I'm Roman. I'm a core developer of a parameter estimation framework, and I do theoretical modeling to figure out why the image looks the way it does.
I'm Lindy. I'm the primary developer of one of our data pipelines. So this is a process that takes the large and complex data sets from our experiment and reduces it down to a much smaller and much simpler set of data that can be used to form the image.
I kind of want to applaud right now, so let's do it. Woo! Now, Sarah, you mentioned that you worked on data calibration. Can you tell us what that is?
So what we record at the telescopes is actually mostly noise. So the calibration process basically is the process of combining all the data and taking out the very weak signal in the recordings and strengthening the signal, modeling the instrument and atmosphere to be able to average down from petabytes of data to all the very nice megabytes of strong signal data that then get passed down to analysis.
That's great. And then, Andrew, you mentioned that you worked on imaging, which I guess is kind of like a next step in the process. Can you tell us about how that works?
Yeah, so we don't actually have the resources yet to build a single Earth-sized telescope. So as Katie mentioned, the EHT is a virtual telescope. We need to devise new software and strategies for converting our data into images and inferring what a single telescope would see.
Awesome. And then, CK, Katie mentioned, and I think you mentioned also, a little bit about the open source components that you used in the project. Can you tell us about your stack? What languages and packages did you use a little bit?
Yes, we use many open source libraries. And once the data hit the calibration and imaging step that Sarah and Andrew just described, we are mainly on a Python stack. So NumPy, SciPy, AstroPy, and Matplotlib are all very important to us.
OK, that's awesome. Now, this team is actually going to be here all day. And they're going to give a talk at 5:20 today on this stage, going into a lot more detail about the project and all the details of everything they did. Thank you all very much for being here. And Katie, thank you again for dialing in from Boston.
Thanks for having us. This team is just the tip of the iceberg. More than 200 people worked on the Event Horizon Telescope team. And as I mentioned last week to Congress, we're deeply grateful to all the open source contributors who made our work possible as well. Thank you.
Let's give these folks a big round of applause. Thank you all very much. Thanks. It's just so cool to have that team here. I've been like fanboying them constantly. So now, as both Katie and CK mentioned, the team actually used a lot of Python code, and they made use of a lot of open source Python libraries in the work that they did. And their code is all public. So we can actually go to the repo and look at it. And we can also look at their dependency graph. And here it is. You can see they've got quite a few different dependencies in the graph. And in fact, altogether, in the complete set of transitive dependencies that made up these Python scripts, there's over 100 different open source Python packages. And some of these are probably used pretty heavily, some used a little less so. But it's a really interesting list to kind of look through. And as we were scanning through this out of curiosity, we started to wonder, how many people did it take to build all of this, right? how many individuals contributed to the full dependency graph that the Event Horizon team used? And so we ran the query, and the number turns out to be more than 21,000 people. It's incredible. 21,000 people around the world were involved in building these scripts. And we have another surprise for you. As it happens, some of those 21,000 people are here in the audience today. And so if you worked on any of these projects, please stand up, turn around, face the rest of the audience. We are so lucky to have with us today maintainers and core contributors to NumPy, Matplotlib, SciPy, AstroPy, Pandas, Python, Dynasty, Cython, Kiwi Solver, and many other packages. These people represent the 21,000 who were part of this extended team that made this work possible. We're so proud to have you all here. Thank you each for your contributions to human progress. Let's give them a big hand again. Thanks, everybody. Thank you all. OK, so the image that needed a planet-sized telescope also really did truly require a planet-sized team to build it. And by the way, at least one of the people who's here, when we called them up and invited them to come, did not know that their work had contributed to the black hole image and was very moved by that. And I thought that was really cool. It's sort of the magic of open source. Now, as Katie said, this is, when you look at the team that's working directly on a code base, in a way you're looking at the tip of the iceberg, right? This isn't just the story of this one software project. This is the story of all software projects today that use open source. So the tip of the iceberg, those direct contributors are the ones who are building your code, but below the waterline are the developers who are contributing to your dependencies. And we've been using the phrase community contributors to refer to these people. They're like the people who are here in the audience today. And one of the things you might be thinking is, well, OK, this Event Horizon team, they wrote their code in Python. They used a lot of high-level astronomy libraries. Maybe they're an outlier, right? Maybe this 21,000 number is atypically high. And we were curious about that, too. So we decided to sample 1,000 of the most popular repos on GitHub, including repos like WordPress and Rails and TensorFlow and others. And we ran the query, and we averaged it all together. And we discovered that on average, these 1,000 projects had more than 74,000 contributors. It's amazing. This is the actual size of our teams, right? Think about it for a second. This is more software engineers than work at Google or Apple or Microsoft. It's actually more people than there are in the entire employee base of 90% of the Fortune 500. And for a couple of you out there, this is more people than the population of Burning Man. So it's a pretty big group. And it's a testament to how software development works today, right? It takes a community to write code. So to make this interconnected community and the reality of this more concrete for each of us in our everyday work, we're introducing 2 new features to GitHub today: community contributors and dependent repositories. So today, if you go to a repo, like this is NumPy, you can see that we actually call out how many contributors that repo has today. Well, we're adding a hover card, so when you bring your mouse up, you can see the total number of community contributors. You can see who they are, browse them, and get to know your extended team. It's pretty cool. Then, we're adding a new signal for you to understand a repo's popularity. So right now, when you look at a repo, you can see how many forks it has, how many stars it has, how many people are watching it. Today now, when we're adding used by, so you can see how many other projects on GitHub make use of the dependencies, the packages that are in that repo. We hope this is a useful signal of a repo's popularity that can help you make better choices. And for you as a maintainer, it's pretty cool. You can see how many people are using your stuff. You can even click on it and see exactly who those users are and which repos that have joined in the last week or so. We screenshotted NumPy a week ago, and it went up by about 1,000 users in the week. So that was pretty cool. So I'm personally really excited about these 2 little features. They're rolling out today. Community contributors is Python first, and it'll roll out to the other language communities after that. And dependent repositories is available for all the languages supported by the GitHub dependency graph. OK, so at GitHub, our mission is to build the global platform for developer collaboration and to make more stories like the one you heard this morning possible every day. And we're really here to serve you. We're here to serve the developers and the companies who count on GitHub every day. And we've been spending a lot of time in the last 6 months in conversations with developers, maintainers, and our customers, and using your input to shape our roadmap. And so today, the new features that we're going to show you are based on the things that you've told us that you want.